So here we have through the fifth excited level, which is numbers 1 through 6. Again, the two don't match up, so be careful about that when reading the textbook and answering the questions. And here we have series, and we try to organize and label the transitions. All transitions to and from the ground state, N of 1, we call that the Lyman series. You have it up there, but I'll write it here as well. I'll add some names to it. So from the ground state to the first excited state, it takes a lot of energy. For example, it takes a lot of energy to blast a rocket ship off the Earth. It takes less energy to move it the same distance once it's off the Earth. The farther away you get from the mass of the Earth, it's easier to move it the same distance. So the biggest energy transition is that first one, going from the first orbit to the second orbit. And that corresponds to a very short wavelength, in other words, high frequency, high energy photon, 122 nanometers. Remember, the human eye sees 400 to 700. Let's put that over here. Visible is 400 nanometers to 700 nanometers. So that first transition is 122 nanometers, shorter than violet, so it's in the ultraviolet. To hop up from the ground state to the second excited state takes even more energy, because we're going from the same place, but farther up takes even more energy, so it's an even shorter wavelength, and shorter wavelength, and shorter as we go to higher and higher transitions. And you can keep going beyond N of 6. It goes all the way. So all those are ultraviolet. So Lyman series absorption will all be in the ultraviolet. And the terminology there is Lyman alpha is the first one. That's the 122 nanometer. The second one in a series is Lyman beta, and Lyman gamma, etc. So we see alpha, beta, gamma, delta, epsilon. Cold hydrogen gas. Most of the universe is hydrogen gas. Most of it's cold, which means the electron is sitting in its lowest energy configuration in the ground state. If we send a continuous spectrum through most of this gas in the universe, you'll get Lyman series absorption. And you can only see it if you have an ultraviolet camera. The human eye won't see that through the grating. But suppose there are all sorts of different ways that you can get into these higher states. Suppose it's already absorbed a Lyman alpha photon and the electron is sitting up in the first excited state. That's one way you can get up in the first excited state. The atom already absorbed the right amount of energy to be sitting up in that higher state. Then all transitions from there on up will be the Balmer series. Another way, we'll come back to it in a second, but here's a more common way to get electrons up into that state. Suppose you have a cloud of gas. At any given time, if it's cold, most of the clouds in the ground state, maybe some things as they absorb light bounce up to these higher states. But suppose you have that gas and you heat it. So it's not a cold cloud, but a hot cloud. Those atoms are going to be moving around, jostling against each other, bumping up into each other. And that's another way you can transfer energy. Here we have two atoms in the ground state, and they're moving quickly because the gas has temperature. They bounce into each other. That energy of motion, kinetic energy, can actually be used to push electrons up into higher states through the actual collision. You don't have to bring a photon to it. You can just run something into it, and the electron can absorb that energy. They got to be pretty hot to do this. So let's say you have gas at about 10,000 degrees Kelvin. Then most of the electrons are in the first excited state. So in that kind of scenario, a hot gas, most of the electrons will already be up in that first excited state. And so then if light passes through, you're launching from the first excited state to the second, the first to the third, the first to the fourth. And these are lower energy transitions because you're already farther away from that central charge. And lower energies, lower frequencies, longer wavelengths, and these come out in the visible. 656 nanometers is red light. Remember, the human eye does 400 to 700. 700 is the red end, so that's going to be on the red side. These other ones are going to be on the blue and violet side. And most of the energy is going from second to third. Second to fourth takes just a little bit more energy. Second to fifth takes just a little bit more. So they start to converge around 400 nanometers. That's all invisible. That's what this looks like. So here we have a Balmer series absorption spectrum. Now we don't write B for Balmer, we write H for hydrogen. They detected the Balmer series absorption first, historically, because they could see it with the human eye through a grating. You had to develop ultraviolet detectors to see the Lyman series. So instead of calling it B alpha, Balmer alpha, they just call it H alpha. So that first transition is H alpha, then H beta, H gamma, and so forth. Got the one in the red, and then converging over here towards the blue. And when you excite the electrons up into these higher levels, give it enough time, and they'll eventually come back down, releasing the Balmer series in emission. And you saw that the other day. I had a tube here. We excited the hydrogen atoms in there electrically, and then they decayed back down to, in that case, the first excited state, and you saw the Balmer series in emission. Okay. Questions so far? I'm introducing concepts and terminology at the same time.
Well, if you heat the gas up even more, let's say 25,000 Kelvin, then you can have, through collisional excitation, you can get up into, let's put notes here, next Balmer series, this is everything to and from the first excited state. Lyman is everything to and from the ground state. If we're up to 25,000 Kelvin, through collisionally, we're exciting all the electrons, for the most part, up to the second excited state. So everything to and from the second excited state, sorry, I'll raise that there, gives you what we call a Paschen series. Now again, you're starting farther away from the charge, so the move from energy to energy level takes even less energy. And these, you can see the corresponding wavelengths are greater than 700. And so this would be in what part of the electromagnetic spectrum? Infrared, that's right. These are, for the most part, infrared photons. And you can keep going. You can imagine a hotter gas. The electrons have been collisionally excited up to the third excited state. All transitions to and from the third is called the bracket series. After that, you have the Fund series, PFUND. After that, you have the Humphrey series, and after that, they're not even named anymore. We'll just focus on these three series, Lyman, Balmer, and Paschen. And they come out in the ultraviolet, visible, and infrared.
Here's another way to look at it. This is an energy level diagram, but the exact same thing. Last time you saw it physically on the atom. Here it is, energy levels. Again, ground state, N of 1, first excited state, N of 2, and so forth. And then on the y-axis is the amount of energy. So as I've been saying, it takes most of the energy to get from the first state to the second state. And then less and less energy to get farther and farther away. Till eventually, it doesn't really cost you any energy to get farther away, and you've essentially escaped. It doesn't require an infinite amount of energy for an electron to escape an atom. It's a certain amount. Just like if we're trying to escape Earth, we launch a rocket with just enough energy, we hit the escape speed, and we're gone. Same thing with electrons. Now, the energy unit doesn't matter. These are called electron volts. You might have seen them in high school chemistry. If not, it doesn't matter. You're not going to be tested on it. It's just a way of measuring energy for electrons. The hydrogen atom, it takes 13.6 electron volts for the electron to escape the proton, hit the escape speed. And again, most of that transition is ground state to first excited state, 10.2 electron volts. Then it's just another 3.4 to escape from that point. But anyway, all transitions to and from the ground state's Lyman, to and from the first excited state's Balmer, second excited state's Paschen, and so on. If you're going up, it's absorption. If you're coming down, it's emission.
And again, it comes out in the ultraviolet, visible, and infrared for those three series. Okay. So this is related to one of the homework questions, question 8, I believe. I've given you enough information to answer, but I just want you to ponder it a little bit. This is the solar spectrum. You take the light from the sun and spread it out from red to blue. This is what you see. Now, the screen isn't wide enough, so this is wraparound. As you read across the first rung, then it's like a carriage return and comes back to the next line. So imagine all these pieces side by side, and that's the solar spectrum. Very high resolution spectrum, so we can see all that's going on here. And there are all sorts of absorption lines, and this is coming from the gas on the surface of the sun. Some of these absorption lines are coming from gas in Earth's atmosphere. Think about it. You got the sun, its surface is hot, it's about 6,000 degrees Kelvin, 5,800, and it releases this light, and it has to travel through gas higher up in the sun's atmosphere, then it travels through empty space, then it travels through our atmosphere to get to our detectors, assuming it's a ground-based detector. So some of these lines are actually caused by absorption by elements in our atmosphere, but most of them are caused by elements mixed into the upper atmosphere of the sun. You have all sorts of things here. You have oxygen, you have iron, you have potassium, all sorts of elements that exist at very low levels. We call them trace elements. The sun is representative of the universe as a whole. It's mostly hydrogen. It's 90% hydrogen by number, 70% hydrogen by mass, approximately. And what's not hydrogen is, for the most part, helium. Those are the two most abundant things in the universe. They're things you get naturally out of Big Bang nucleosynthesis, something we'll talk about in Astro 102. Everything else was made in the belly of stars. Carbon, nitrogen, oxygen, the stuff that you're made of, was made in the bellies of stars as fusion progressed, and some of those stars exploded, scattering those elements throughout space. Eventually, they get incorporated into other stars that produce more of those heavier elements, and they explode. You yourself have been through 50 supernova explosions to make enough stuff to actually make you. Because the stuff we're made of and the Earth, doesn't exist at the beginning of time, only the hydrogen and the helium. And it's still the dominant thing in the universe. Given that, you might expect that the dominant lines here would be hydrogen and helium lines. And they're not. And let's focus on the hydrogen, since we talked about that in great depth here. We see oxygen and iron and all these other things, and there are some hydrogen lines here. They are not very dominant. Why would that be? Why don't we see hydrogen lines if the sun's primarily hydrogen? Yes? Exactly. It's the temperature of the surface of the sun. The sun we think is really hot, but the surface is only 6,000 Kelvin. Yeah, it'd burn you to a crisp, but it's below the 10,000 Kelvin that's necessary to collisionally excite the hydrogen into the first excited state. So even though it's hot, those atoms still exist in the ground state on the surface. So as the light's coming from beneath, light that's generated in the core through nuclear fusion works its way out of the sun over a long period of time. It takes, I'm trying to remember the exact number, but like a couple 100,000 years for light to actually work its way to the surface. And then it passes through this gas that's in the ground state. And so what kind of series do you get if the gas is in the ground state? Lyman. And that can only be detected in the ultraviolet. And this is the visible part of the spectrum. If we were to continue it out into the ultraviolet, you would see whopping strong absorption lines corresponding to Lyman series. But this is just the visible part, and so you don't see it. Now, if I was looking at a star that's 10,000 degrees, the surface would have already been excited into the first excited state, the electrons. So when the light passes through, you would get a Balmer series, and it would be the most dominant signature here.
So spectroscopy, spectral lines, give us composition, but they also give us temperature. We can also get the temperature from the continuum emission. We just see where it peaks in the red and the blue, the color of the star. So from the continuum we can get the temperature. From the absorption lines we can get the temperature and the composition.